Good afternoon. I am Mr. Rich. Thank you for joining me and for watching my videos. We are looking here an interesting video because we are breaking away from the normal topics of calculus and taking a little tour of geometry utilizing this challenge we have before us. We're looking here at an inscribed polygon in a circle, and that right there will be the challenge. Specifically, the challenge will be this. If you have a good circle and you draw within the circle an equilateral triangle, how can you determine the diameter of this circle? Generally, if you have a circle and you have an inscribed square, it's very easy to determine the diameter of the circle because the diagonal of the square represents the diameter of the circle, and it's easy. If this right here is x, that's x. You know you're gonna use simple trigonometry or geometry and you can get x root 2 to be the diameter of the circle and the diagonal of the square, and that part is done, and it's so easy. But the challenge arises when rather than a square we have a triangle in here. Each of these sides of this equilateral triangle are not diameter by any means, because the diameter is a chord which goes through the center of the circle from one end to the other, and none of these chords are going through the center. So how can we use the sides of an equilateral triangle, assuming the side is equal to x? How can we determine a formula for the diameter of this circle? And it would be a good challenging exercise. What do we know offhand? And let's list it out. We know an equilateral triangle or an equilateral triangle has three equal sides, and each side over here of this triangle is equal to x. Since there are three equal sides, there are three equal angles. Each angle of this triangle is equal to 60 degrees. And what else do we know? If you're looking at a right triangle and you're talking about trigonometric ratios with regards to 60 degrees, you know you have these type of values and ratios pop up. And the most important in terms of trigonometry and the trigonometric function for this exercise will be tan of 60 degrees will be root 3 over 1. So that's a value we'll set aside in our minds. We have to remember that. And another thing we know is this specific property. At any point of a circle that you have a diameter and you draw a triangle from this, from one point and the other point, anywhere on this curve, you're connecting from one point of your diameter to this point right here, you've arbitrarily picked or selected on your arc, and you take it on the other side, you're always creating a right triangle no matter where that point might be. It'll always end up being a right triangle, even if my diagram is not showing you that, but it'll always be a right triangle no matter how you look at it. So keep this specific property in mind because it will come into play in the determination of a diameter of this specific exercise we have. Alright, so let's actually solve this challenge. The challenge is this: we have this equilateral triangle and we have to determine the diameter or the formula for the diameter of this circle. If we know that each side is x and we know each angle here is 60 degrees, because it's an equilateral triangle, all angles must be 60 degrees. So how can we start and how can we proceed? How about we just draw a diameter right in the way we see it and we create these two right triangles. The hypotenuse of one of these right triangles ends up being an x. This right here is also an x, but it's been split into two halves by this bisecting line. We have an x over 2, and we know we have a right triangle here when we have 60 degrees over here. We can use a square plus b square is equal to c square. How about we call this h? We know h square plus this other length square is equal to that square. We take everything on the other side and solve for h. We have x square minus x square over 4, and h square is equal to 3x square over 4, and h is equal to, you can just say h over here is equal to root 3x over 2. What has that told you? That's given you the length of this height, and let's write it out. We have now this side over here, root 3x over 2. What remains now, since we've determined already this part right over here, all of this, what remains now is the determination of this. All you have to do is add that to this and you'll have your diameter. But how can we go about doing that determination? Well, now we think back to that rule or property I told you earlier. We'll connect this to over here. And now we have connected from the ends of a diameter to somewhere on this arc. A point has been connected by two lines, and therefore this now has generated in 90 degrees. And that exactly is why I brought that up. If you look at this, you have a 60 degrees here, you have a 60 degrees here, but you have a complementary angles over here. So this right here must be 30 because This right here was a 90, that right here was a 90, that was a 90, 60, 30. If this right here is 30, then this right here has become a 60 degrees. Let's pluck out this triangle and draw it exactly as we see it. We see it in this way. We have a 30 degree over here, we have a 60 over here, and we have a 90 degrees here. We have this side over here, which is x over 2. Remember, this whole length x was split into an x over 2, and we don't need anything else, and we're only solving now for this part right here. We can use trigonometry to do that. If we're trying to determine this over here, we can use tan 60 degrees. Tan 60 degrees is equal to this side, x over 2, which is opposite to that angle, divided by adjacent. We'll call this h2. h2 is equal to x over 2 divided by tan 60, which is root 3. h2 is equal to x over 2 root 3. Now we've gotten the side here, h2 is equal to x over 2 root 3. Let's draw out this entire diameter now. We have this entire diameter. From here up to here, it was root 3x over 2, and that's what we determined. Then for the second part right here, it was x over 2 root 3. So the total diameter over here must be the sum of these two, and we just have to add them up. Root 3x over 2 plus x over 2 root 3, common denominator would be 2 root 3. 2 goes into root 3 times, which multiplies with this, you'll get 3x plus x. You'll get a 4x over 2 root 3, and you can simplify that. You'll have 2x over root 3, and that right there will be the length of a diameter. For any equilateral triangle inscribed within a circle, you know triangles are polygons. An equilateral triangle inscribed within a circle having a side x will generate a circle having a diameter 2x over root 3. So if an equilateral triangle hypothetically had a side equal to 6, where side is equal to 6, then the diameter of the circle within which it is inscribed would be 2 times 6 over root 3, and the diameter will be 12 over root 3. And that right there is what you would have in terms of a numerical value for a diameter. But this value over here in terms of the length of the diameter for an equilateral triangle having sides of x, 2x over root 3, it's good, and I've shown you how we went about doing it. We first determined this, then we determined that, and we added them up. And you saw how this property came into play. You saw how tan 60 came into play. And with that, we end this video. Hopefully you enjoyed this challenge. Thank you for watching. Have a nice day.